This is the first of 3 videos regarding the scientific complex data array calculator. Once invoked, the calculator always has a help message. Enter mag and angle or recall a data set. Data set would be recalled from one of the registers. Toggle mag to enter an angle. For example, let's say that we wish to add 1 at an angle of 0 degrees plus 1 at an angle of 90 degrees. We all know this answer. It's 1.414 at an angle of 45 degrees. Complex numbers can be multiplied by arrays. Arrays can be multiplied by other arrays provided they are the same size and shape. The special function keys offer the standard square root, log 10, natural log, 1 over x, pi, trig, and constants, conversion constants, and we'll see how that's used. In addition, since all DAMS data is linear, a data set which might contain match data can easily be converted to VSWR. Return loss can give you an idea of how much gain has been lost or how much would be achievable. Anything dB goes exactly to dB, converts either an array or a display to 20 log voltage. The angle is set to 0 since there is no complex dB. dBd is dipole gain. Max will invoke the maximum for whatever array is resident in reg 0. It also sets the elevation and the azimuth sliders to the associated as-L. Little max, lowercase max, works only on the single line of display data. Clip is the same clip function that was present in the original data calculator, except that it's now Boolean. When clip is invoked, this will clip reg 0 to a value less than the expression results, and the expression results are any mathematical expression terminated with the equal sign. Inverse clip sets the Boolean to greater than the value. And this is very useful for beams and high gain antennas. So we're going to clear the screen and we're going to perform the last macro button, which is wavelength. Wavelength determines from whatever frequency is entered the existing wavelength in units of path loss. The default path loss units for the DAMS is meters, and that's the current setting. So if we enter 1E9 hertz or 1 gigahertz and invoke wavelength, we get 0.3 meters. And we all know that that's the correct answer. If we inverse, we get 1E9, 1 gigahertz. We'll go ahead and clear the calculator and we'll load the dipole file, always resident in advanced data, and we'll recall the predetermined gain profile. And here we see the frequency across for the current azimuth elevation slider settings. If we change the settings, then we change the numbers. If we wish to perform a math function on the as-else setting, we may do so directly. The dB values are 2.35 dB. Once that's done, the data array has been changed, and we need to recall the original data array. If we wish to export to reg0 a math function on the data, then we check results. The elevation sliders are grayed out. The entire data array will now be operated upon. At this point, if I invoke dB, it's now in reg0. I could save it over to a reg, and I could be sure it's there by clearing the calculator, recalling the original data, and recalling the new data. That's a very easy and direct method of performing math functions. Because the math is complex, all of the math functions that handle complex are valid. If, for instance, I recall from the dipole data the match, I can immediately convert this to VSWR with the VSWR button. And if I go and plot the data in the polar plot or the simulator, I'll have a VSWR plot. If I inverse VSWR, then I get the data back. But I've lost the angle because VSWR has no angle either. We enter 1 meter as a complex number, and we wish to convert that complex number to inches. We'll take 1 meter times the conversion constant, meters to inches, 39.37 inches. So it's a time-saving macro. The clip function enables the same process as was done originally in the simple calculator, but it's Boolean oriented. If, for instance, we recall a measurement set and we wish to clip that measurement set, now it's telling us the Boolean and how to do it. We wish to clip that measurement to 0.1, pressing equals invokes the clip, and we see 0.1 replaced all numbers that were smaller. And if we do inverse clip, we can do the reverse. This covers the basic functions of the scientific array calculator. One caution is not to try to perform operations on different sized arrays. In some cases, the results will occur, but they'll be incorrect. In other cases, the complex calculator will shut down and tell you that it needs to be restarted.